Hello, I'm Divya Srivavi, working as Assistant Professor in the Department of ACE SJBIT. In my previous video, we have discussed about the modulation, the communication system, need for modulation. In today's topic, we will be discussing about the amplitude modulation. So first, we will understand what is modulation. It is the process of varying the characteristics of high frequency carrier in accordance with the instantaneous value of modulating or message baseband signal. Or you can also frame it is a frequency translation technique which converts baseband or low frequency signal to band pass or high frequency signal. So where do we use this modulation? It is used in the transmitter. First, we'll understand what are the types of modulation available. The first, broadly, we can classify the modulation as two types. One is continuous wave modulation, another one is the pulse modulation. Continuous wave in the sense analog modulations. So here we have two things. One is amplitude modulation, another one is angle modulation. Amplitude modulation is a technique where amplitude of the carrier is varied, and in angle modulation the frequency and phase are varied. So angle modulation, again, it is broadly classified into frequency modulation and phase modulation. Coming to the second category of modulation, that is pulse modulation. Here we can broadly classify this as analog modulation and digital modulation. Coming to analog modulation technique, it is classified as PAM, pulse amplitude modulation, pulse width modulation, and PPM. Next, in the digital modulation technique, we have pulse code modulation PCM. In that, we can understand what is the delta modulation. So, in brief, this is the modulation types available, and this is the categories. So, we understood what is modulation. We are varying the characteristics of a wave, and it is found in the transmitter side. So now we will understand what are the different types of modulation available. One is amplitude modulation. So here in amplitude modulation, amplitude of the carrier is varied in accordance with the instantaneous value of the modulating signal. So only the amplitude characteristic is varied. The frequency and the phase is kept constant, means it is not varied. The second type of modulation is frequency modulation. Here frequency of the carrier is varied in accordance with the instantaneous values of modulating signal. So here only component which will be varied is frequency. Amplitude and phase will be kept constant. The third category is the phase modulation. Phase of the carrier is varied in accordance with the instantaneous value of the modulating signal. Here amplitude and frequency is kept constant. So these are the three types of modulation available. In the syllabus first module, it is related to the amplitude modulation. So we'll take up the AM now. Before going with the AM, let us just have a recap on what are the need for modulation. What is the benefits of modulation? It reduces the height or the length of the antenna. In the previous video, I have explained the minimum height required is lambda by 4, and when you start increasing the frequency, so the height of the antenna will be decreasing. So there is a need for converting a low frequency message signal to a high frequency signal by combining it with the high frequency carrier wave. In turn, we are sending a high frequency wave. In turn, it reduces the height of the antenna. It avoids mixing of signals. It increases range of communication, allows multiplexing, bandwidth adjustment, and it improves the quality of the reception. All these points are already been discussed in the previous video. So moving on, the amplitude modulation. So here the amplitude of the carrier is varied in accordance with the instantaneous amplitude of the message signal. Whatever you are seeing here, this is your M of t. That is the message signal. M of t is a message signal, and let us represent C of t as the carrier signal. You can also call message signal as a baseband signal. The frequency modulated signal, let us represent it as S of t. That will show it in a next slide. So here if you observe, the frequency of the message signal or a baseband signal, it is very much less compared to the carrier signal. So we should choose the frequency of the sinusoidal carrier signal in such a way that it is much higher than that of the modulating signal. And now what happens is the amplitude, if you see, it is constant in case of the carrier signal. As and when the message signal amplitude varies, now the carrier signal amplitude also varies. Amplitude of the carrier wave, it is varied in accordance with the modulating signal. Frequency and phase will remain constant. So you can see this is represented as S of t, the modulated wave. The amplitude or the shape of the modulated wave, it resembles to the message signal, and this is basically a carrier wave frequency, C of t frequency. Amplitude is M of t. It is similar to M of t. So what happened here is the carrier frequency, now its amplitude is varied in accordance to the message signal M of t. So this kind of applications, that is modulation, it is used in applications like radio transmissions, TV transmissions, etc. Now how we can represent the amplitude modulation in time domain and frequency domain, in brief we will understand. Let us represent the carrier signal as C of t is equal to AC into cos omega ct, or you can also write this as AC into cos of 2 pi fct, where omega c is nothing but your 2 pi fct. If you are representing the frequency in hertz, then it is 2 pi fct. If you are representing the frequency in terms of radians per second, then it is omega ct. So what is C of t? It is the carrier signal. So what is AC? AC is the maximum peak amplitude of the carrier signal. FC is the carrier frequency, which will be represented in hertz. WC is nothing but your 2 pi fc, that is the frequency of the carrier signal. So this is about the carrier signal. Now the modulating or baseband signal, you can also take this representation as M of t or X of t. M of t is equal to Am into cos of omega mt, or you can also take this as Am into cos of 2 pi Fm into t, where Am is the amplitude of the baseband signal and Fm is the frequency of the baseband signal. So how do we represent the amplitude modulated signal is the standard equation is given by S of t is equal to AC into cos 2 pi fct into 1 plus MA into cos 2 pi fmt. Here they have represented or used the message signal in the equation. In general, you can take this as S of t is equal to AC uh, cos 2 pi fct into 1 plus Ka into m of t. So what is this Ka is? Ka is the amplitude sensitivity of the, or you can also call this as a modulation index of modulator, which is responsible for the generation of the modulated signal S of t. The carrier amplitude AC and the message signal m of t is always measured in terms of volts, and Ka, it is always measured in terms of per volts. So here in this equation, the term that is AC and 1 plus Ka into m of t, that gives the instantaneous amplitude of the modulated signal. We also call this as the envelope of an AM wave. So 2 pi fct, this term. So this is a carrier wave which shows the frequency of the AM wave S of t. And you have to recall that if this wave S of t will be having the same carrier frequency as that of Fc. So now we will see the time domain representation of AM wave. C of t we have already seen, it is AC into cos 2 pi fct. This is the standard equation. S of t is equal to AC into cos 2 pi fct into 1 plus Ka into m of t. So where AC into 1 plus Ka into m of t, it forms the envelope of a AM wave. So depending on the term Ka into m of t, so this term, it actually it is called a modulation index. We also denote this by the term mu. What is mu? Modulation index. So when Ka into m of t, that is modulation index, when it is very much less than 1 for different values of t, what happens is 1 plus Ka into m of t will always be non-negative value. So 1 plus Ka into m of t means it is always greater than 0. So what happens is you will get the maximum absolute value of Ka into m of t, which is multiplied by 0. We define that as a modulation in percentage. For any value when Ka into m of t, if it is less than 1, means less than 100%. So this type of modulation is linear amplitude modulation. When Ka into m of t is less than 1, means it's a linear amplitude modulation. When Ka into m of t, when it is equal to 0, means it is 100% modulation. When Ka into m of t, when it is greater than 1, means more than 100%. In that case, we call this as a over modulation. So we also call this as phase reversal of the envelope. We will see this concept afterwards. So let us analyze how do we get the time domain representation. So it is AC cos 2 pi fct plus mu AC by 2 into cos of 2 pi fc plus 2 pi fm into t plus mu AC by 2 into cos of 2 pi fc minus 2 pi fm into t. So whatever the first term we are saying, that is the carrier signal with the amplitude AC and at the frequency Fc. The second term is at the frequency Fc plus Fm. We call this as upper sideband, and it is having the amplitude of mu AC by 2. And this third component is the lower sideband, which is having the amplitude mu AC by 2 and frequency Fc minus Fm. So when we use the time domain representation, that's how we see the equations. Next, the amplitude modulation in frequency domain representation. So in frequency domain, what we do is, whatever the equation we have in the time domain representation, we take the Fourier transform on both the sides. Then we will get the frequency domain of the signal. So this is the equation for S of t in time domain. S of t is equal to AC into cos 2 pi fct into 1 plus ma into cos 2 pi fm into t. So taking the Fourier transform on both the side, will get S of f is equal to AC by 2 into delta of f minus fc plus delta of f plus fc plus AC ma by 2 into m of f minus fc plus f plus fc. So suppose if you take the message signal m of f of this shape, which is distributed between minus w and plus w, that is the bandwidth 2w. So its representation of S of f, that is the after taking the Fourier transform, you will get S of f. So that we can represent as in the spectrum form as this. So you have two components, one is at minus fc, another one is at plus fc. So at minus fc you have one delta function, so which is having the amplitude AC by 2, and at minus fc you have a message signal that is having both lower sideband and the upper sideband. Since the shape of the message signal is like this, so here also like this. So the width is fc minus fc plus w to minus fc minus w. Coming to the frequency fc, it is distributed from fc plus w, fc minus w. So this is the frequency spectrum of AM wave in frequency domain representation. So what is the modulation index? Basically you have three components. One is at fc, another one is upper sideband, another one is the lower sideband. So the maximum frequency will be f max plus f max is equal to fc plus w. The minimum frequency is f minimum is equal to fc minus w. Modulation index is given by AM by AC, or another formula to calculate the index is A max minus A minimum divided by A max plus A minimum. If you are expressing the values in percentage, it is taken as percentage MA is equal to A max minus A minimum divided by A max plus A minimum into 100, nothing but AM by AC into 100. So this is what is the three cases what I have discussed previously, that is depending on Ka into M of t. Here they have taken as MA. If modulation index, if it is less than 1, under modulation. If it is equal to 1, critical modulation. If it is greater than 1, over modulation. These are the three aspects of modulation depending on the modulation index. So how do the waveform looks like when we have different modulation indexes? In the under modulation case, when MA is less than 1, so you can see a mere modulation taking place, variation in the amplitude. Whereas in the critical modulation, when it is equal to 1, you can see there is a flat line when you have a minimum amplitude. That is the critical modulation. When you have the over modulation, what happens is there will be a phase reversal at the minimum side, and there will be a side lobes like this, a major envelope and a minor envelope like this. So this is the condition with respect to the over modulation. So there are two types of methods to generate the AM wave. One is square law and switching modulator. Two methods are there, but in the syllabus we have the switching modulator. So in my next video I'll be explaining about the switching modulator and certain equations related to that. Let me brief about what all things we have discussed in today's lecture. First thing is, we have started with the modulation, types of modulation, need for modulation, what is amplitude modulation, then what are the equations for the message signal, the carrier signal and the modulated signal, and how do we represent it in time domain and the frequency domain. Based on the modulation index mu, how the amplitude modulation differs from one case to another case. So there are three cases when the modulation index, if it is less than 1, under modulation, equal to 1, critical modulation, greater than 1, over modulation. So after understanding all these things in time domain and frequency domain, we will move on to the generation of AM signals. How do we generate AM signal? These concepts. Thank you.